Yes. I've been away from this class for a month, and I'm back here again for the part 3. As we know, this course consists of 3 parts. One was the kind of elementary thing, some kind of statistics knowledge, mostly about the Bayesian. And the second part was taught by mostly by Professor HAFTKA. And the third part we are beginning now. And the reason for the first part was to apply the techniques, statistics techniques to this verification and validation topic. And we know that the title of this course is about this. So this is the most important, and this was the target for the course. And this is the newly established course. So I told you a couple of times that I'm not prepared to make this course in a well-established form. So from time to time, the topic is changing constantly. So even in this case, the part 3, the procedure was changed a little bit. After thoroughly reading the textbook made by Oberkamp and Roy. And the red parts I teach, and the purple part Professor HAFTKA teach. And I will today explain some outlines of the validation and also the calibration. And from that time, I will move to the specific details one by one. And I think that Professor HAFTKA will cover some global picture of this verification, validation, uncertainty quantification. And he will also in charge of the verification to some extent. And the other part I will cover. And I am mostly responsible for the calibration, validation, and the implementation of that using the statistic techniques that I taught in the first part. And I have to admit that despite this, some overlapping will be occurring, and I ask your understanding. So this is today's outline. Even in the first part, when I began the very first lecture, the class, I introduced what is the Bayesian statistics at that time. And from that time on, I moved to the specific details. And this is the same thing. Today, I will overview the procedure and the concepts of the verification, validation. And from the next class, I will step into the detail. So the first part I will talk today is about some issues surrounding the verification, validation, which is also which is another thing. I can say this as why do we have to care about this? And this can be explained by these 2 things. Next, I will show you some kind of a validation definition and the procedure. And also, I will explain some recent activities related with this V&V. There were recently some workshops in the United States. And also, there are short courses provided worldwide. So I will talk a little bit about that. And there was also the challenge problems back in 2006. And this was very, I think, very helpful. So I will talk about this to you for a better understanding of the V&V. Also, I will talk about this too, just one page, because they are also preparing another version of the challenge problem. And if time is allowed, I will also talk about this. So first one is the issues surrounding the verification validation. And there, I have two questions here. And these questions were brought from this paper. It was in 2002. And I think this is also a famous paper in the field of verification validation. And there were many authors with this paper. And consists of two groups. One group from the statistics, working in the National Institute of Statistical Sciences. And the other group are coming from General Motors. So they are a combination of the theoreticians and engineers. And they made these two questions. First one was does the computer model adequately represent reality? And the other one was, what if the computer model differs from the field data? So these two issues I will explain a little more detail in the next page. And the first issue, I can also say that as the title here. So the first issue was, does the computer model adequately represent reality? That we can say in another way like this. We'd like to evaluate the validity of a computer model. And this is a very straightforward statement. You know most of these. We have a very good computer model these days. And the computer model, unless it is validated, is useless. We know that. And there was another example that illustrates this point. And this was made by this doctor and in this conference. And for this specific example, the topic was to analyze the projectile impacts against the composite plates in this airplane. And this is a kind of a state-of-the-art technology to analyze using the finite element analysis. But we soon find that we need this many input parameters to make the simulation. And we will agree that unless we have correct values of these input parameters, the results will not be good. So that's why we need some kind of validation every time when we talk about the good computer model. In that case, the question should be not this kind. Is this model correct? We should not ask like a black and white question. We should not ask like a yes or no question. In this case, we have to ask like how accurate is the model for our problem. And the answer should be like that, the tolerance bounds or confidence bounds. Something plus minus another thing. And this will be the final results after you have studied this course. There is one more thing about this. Another interesting viewpoint. When we say about the validity of the computer model, we should be a little bit cautious. And there was a famous saying made by this authors. They say essentially all models are wrong, but some are useful. And the scientists, even with this, scientists tend to focus on whether that is true or wrong. And from engineers' viewpoint, we don't care about that. We just care about how accurate is this model. And this is a good example from a Greek astronomy. And there was a very false belief on these things in the ancient times, that the Earth is fixed at the center and the others move around. We all know that this is wrong. But even at that time, they made a computer model, not the computer model, they made a model, and they used this, and the remarkable accuracy they got. And from engineers' viewpoint, this is very good. From scientists' viewpoint, this is wrong. So I'd like to say this difference and this viewpoint in terms of the validation. The second issue was about this question. What if the computer model differs from the field data? We can consider, for example, these cases. Naturally, when it comes to any difference between the two, the computer model and the reality, we will check and compare the two results. That's very natural. And the thing is that we get these kind of situations. The first, we make experiments and get the data. And we make a simulation, get output. They close each other. So our conclusion is good. We have agreement. But in fact, there was some uncertainties, as we all know. The test also has the uncertainty due to some kind of error. So the realized result was this. In the simulation, the same thing. It was like this. And in fact, the simulation mean, test mean, very big difference. But we come to the conclusion that the two are close each other. This is the opposite case. They are, in fact, close with each other, but turned out to be very different. So we should avoid this situation. In order to avoid this kind of situation, we need to consider the associated uncertainties in the both cases. And what we care in this course is not about the experimental data. We assume that the data includes the errors for whatever reason, measurement, randomization, and we take it as granted. What we care, what we are interested in this course is about the model. I'd like to explain how to make the how to account for the uncertainties in the model. That's our goal in this course. And in order to do that, we need to have obviously the computer model. Originally, this is deterministic. Whenever we have a certain deterministic input, we have a single value of output. But in fact, all the input parameters have some kind of uncertainties. So we need to characterize those uncertainties and put those into some kind of form of a probability distribution or others. And take this into this model and we get the output. And what we get is not the single value, but the another distribution of the output. And we call this as the uncertainty quantification. So I am not quite sure whether this is explained by Professor HAFTKA. I just summarize the uncertainties surrounding these issues. You will see without any difficulty the types of these uncertainties here. At first, we have a measurement uncertainty for the experimental data. And we'll also have a statistical uncertainty due to the lack of the test data. We don't have enough time usually. So we have only limited resources to have data. In that case, we cannot say using only a few number of data, or 5 or 10, we cannot say this is normally distributed. This is the mean of this distribution is this. In order to do that, at least we have to have more than 30, 50 number of data. But that is not the case in reality. So we say it's statistical uncertainty in that case. Third is the physical uncertainty. There is an inherent material variability. We all know that. Also, there is the environment that we cannot control. The loading spectrum or something else, temperature, we cannot control them unless we do it in the lab. But the reality is in the field, and we cannot control that. So we have to model those uncertainties in whatever way, and we say that as the physical uncertainty. And there is also the model uncertainty. In case of the probability model, when we say this follows the normal distribution, we cannot be sure. This could also follow the other type of distribution. And when we choose one among the others, we have that kind of uncertainty due to the choice of a certain distribution. Also, there is uncertainty due to the modeling assumptions. In case we employ the drag is proportional to the quadratic velocity, or we can also model that as the linearly varying with respect to the velocity. That's our assumption. And there comes the uncertainty due to that. Model selection, the same things. Also, when we employ the surrogate model, approximate model, because the computational model is costly, it takes a very long time. In that case, usually we introduce surrogate model, and there comes the uncertainty due to that. So these things are about that. And depending on the parameters we use for these uncertainty, we can group them into this. Input uncertainty is about the material, dimensions, and boundary conditions. In the model uncertainty, I told you here, things like this, the physical model assumption. And the third one is about the verification, some kind of a numerical solution error. And in terms of the type of the uncertainty, we can also classify these into these two. The first one is the aleatory uncertainty. We say this as the inherent randomness. It comes from inherent randomness. And we call this as the irreducible. Yes?
I was just wondering which category would something like manufacturing uncertainty fall in the first?
Yeah, when we say the manufacturing uncertainty, I would include it in the physical uncertainty. It cannot be reduced. Someone could say that the other way. If we tackle the manufacturing problem and reduce the uncertainty in the manufacturing process, that could be reduced. And I am saying it cannot be reduced. So that could be some difference with that. But it depends on the how we see on that uncertainty. So when we say about the lh11 uncertainty, we have to say it is not reduced. It cannot be reduced. And it includes the material variability and uncontrolled environments. And the other one is the epistemic uncertainty, comes from the lack of knowledge, lack of data. So if we increase some more data, we can further reduce that uncertainty. And if we have some more consideration of the model selection or assumption, we can reduce that uncertainty further. So that is called the epistemic uncertainty. This figure came from the textbook, and I searched whether Professor HAFTKA used this or not, and he didn't use this. So I am happy to explain because it's not overlapped. And this figure is another very obvious explanation of what is the validation. We have a computer model, we have experimental data, and there are the outputs from the two sides, and compare the difference. If it does not agree, we have to make some action until it gets the agreement. So this figure explains that thing. And once we have the agreement with this model and experiments, no. Once we have a disagreement, once we have a difference between the model and the data, we have to feedback in two ways. One way is to check whether any experiment was wrong, or if possible, we add some more experiments and get more data. And the other way is to, in the side of model, computational model, in this case, we have to also check whether this model was correct or not. But based on our assumption that the model itself is correct, the next thing we have to do is whether we input parameters correctly. And in most cases, we have the parameters that are unknown, that are not easy to assume or assign values. So in that case, we have to calibrate the model based on the experimental observations. And in that sense, we will get agreement because we calibrate based on this. So we intentionally make agreement using tuning some unknown parameters. We say that as the calibration. In that case, we already get the agreements. And the last thing we have to do is to use this model because this is already calibrated. We can use this model safely for the future prediction at untried conditions. Sometimes it's kind of a interpolation or extrapolation, not at the existing data, but at the untried conditions. And this is our target. This should be correct. And in order to validate this, we have to have one more stage of the validation at the untried conditions. And the textbook recommends, they call the blind prediction. They have the data at the new experiment, and they don't give the computer guy this result and let them predict it. And if they get the agreement, they are doing fine. Otherwise, something wrong still. So this is called a predictive validation. So I will explain the three important keywords as I show you here in the next slides. First one is the calibration. In case we don't have any agreement between the two. And the next is the validation, the comparison between the two. And the third is the predictive validation. So the calibration. Already told you that some model parameters not easy to characterize or measure or assume. In that case, the thing we do is calibrate inversely from the output, from the experimental data. The famous example is about this, the damping coefficients, stiffness. Sometimes this is hard to characterize of the joints in the structure, and this is very critical when we analyze the vibration of a structure. Very critical thing, and it's not easy to characterize. So they, most of the case, they inversely calibrate these parameters. Thermal contact resistance, another thing. You can imagine how difficult it is to characterize. There is a very microscopic voids and gaps, contacts, never easy to characterize. But the analysis, the computer model requires this information. So in any way, we have to put some value on that. Very tricky problem. So the conclusion is arbitrary assignment leads to model inaccuracy. So the calibration is the activity that inversely estimates based on the experimental observations to find out the unknown parameters. So this is also called like this, the pre-validation, to improve agreement between the two by inversely estimating this. Also, this is known as the parameter estimation. There are many other similar names that represent the same thing. Model tuning, model update, all these are the same things to express this. And there are some remarks for this calibration. Sometimes, this is from the textbook, the Oberkamp's textbook. Yes?
So, when you are fitting some kind of a response surface or surrogate model, is it also part of calibration?
In that case, when we introduce surrogate model, can we calibrate still with that model? Is that your question?
I mean, yeah.
In that case, the surrogate model, originally, the computer model is some kind of a symbolic expression like this. And in case that we have some unknown parameter, we add parameters in this way. This is some kind of parameters like thermal contact resistance, things like that. And this is another input that is well characterized parameters. So we can group the input parameters in these two groups. And when we introduce a surrogate model, this is turned into some kind of other function of theta. So in terms of theta, we have the surrogate model, and we have the experimental data. Then we can inversely calibrate this unknown theta based on this data. So when we introduce surrogates, the procedure will be like this. Yes, even in the surrogate model, the calibration applies the same. So we apt to think that the calibration is the same as the validation, but we have to make strictly the difference between the two. And the validation can be made without calibration. So I would like to say the calibration is a kind of an additional step in case we don't have any agreement. And if we have the additional calibration step, we have to be careful. In that case, it should be made before the validation. And the data, experimental data used for the calibration should not be reused in the last step. I told you there is one more step about the predictive calibration. Once we have the calibration step, we need one more step of that. And in that case, we should not use the data. It's very ridiculous. Because the data was used for the calibration, it should not be used for the prediction. This is the thing. And the part one. More than a month and a half, we spent time for the Bayesian statistics. And the techniques are very usefully applied in this case. The parameters like these, unknown parameters, are calibrated after making the posterior PDF for these. And you can use whatever method we studied, like Markov chain, Monte Carlo, whatever. Once we have the established posterior PDF based on the observed data, in this case, it's experimental data, then we can make samples that satisfies this distribution for the parameters. And using these obtained samples, we can make the posterior prediction. This is exactly the same thing that I showed you, the predicted validation. So we can have very good analogy between the thing we learned and this. So next is the validation. Validation is another name of the model accuracy assessment. So even the title of the chapter in the textbook is not the validation. The title of the chapter 12 is the model accuracy assessment. The same name, same meaning. In this case, we have to introduce the validation metric to quantitatively compare, not just qualitative. The reason is because from now, we have to compare distribution versus distribution. We know that the experimental data is already distributed quantity. And also the computer model, because I told you it should be turned into the stochastic, not the deterministic. So we have the two kinds of distribution, one from experiment, one from the computer model. How to compare and how to make conclusion with those. That is the thing in the validation. And once we go through the validation, and it is found to be validated, then we move to the predictive validation. This is the thing. I told you several times before about this. And you see the blind predicting. I told you about this meaning. The computer guy should predict without getting the knowledge on the experimental results. And only after that they make comparison. There were recent workshops, short course tutorials related with this topic. So I think that this topic is very hot in this field, including mechanical. I'm not talking about the computer science engineering. I'm talking about the mechanical and aerospace engineering. In this field of engineering, there are many active workshops, things like this recently. And this is the short course provided. It will happen this December in Germany. And this is happening in the Europe. And there was also another tutorial in this society, the PHM society. The PHM represents the prognostics health management. It's about the kind of a maintenance engineering, and the topic that I'm studying actively now myself. So I attended the conference in 2009, and there I could take the course provided by this Dr. Hemetz. I'm not sure how to pronounce this guy, from France. And he's working in the Los Alamos lab, and you can find his name in by searching it in the Google. And he claims that he developed the first verification validation course in the University of California, San Diego. And I don't know whether that's true or not. And I thought the Professor HAFTKA is the first who makes the graduate course in this topic. And there was also, I told you that the challenge workshop, they made a problem that the people can solve in terms of validation. And they gathered in a place in Albuquerque, 2006, and discussed each other, communicate their methods, and published their work in a journal, special edition, Computer Method and Applied Mechanics Engineering, in 2008. So I will explain just one example of that here. And they are planning another challenge workshop. So that means they are preparing another challenge problem so that the people in this field can solve by their own technique and gather around and discuss each other. The first V&V symposium held in last year. And this is the second year of this symposium by the American Society of Mechanical Engineering. And it was very good to find there is a site at the bottom line. You can get access to there, and whatever kind of a presentation papers, all can be downloaded from there. Very good stuffs are there, including the plenary lecture by Oberkamp. So this is about the challenge problems 2006. There were 3 problems: thermal, structural, and structural mechanics and structural dynamics. And they provided experimental data for each of the problems. But it was synthetic. It was fictitious, not the real data. So that was the thing that made through the simulation and intentionally put some noise, assuming that is the experimental data. And participants took these problems and solved and gathered in one place and discussed. Their problem statements for all the 3 problems, their problem statement was like this. They introduced a target problem to be solved. I will show you what this is in the next slide using the thermal problem. And they provided 3 types of experimental data. Bottom level, the material characterization, like thermal conductivity, Young's modulus, things like that. They didn't measure directly. They just fictitiously generated. At this level, of the experiments, we can make many data because it's not expensive. We just prepare coupon and measure. Next level was the what they called ensemble experiments. I don't know why they call this as ensemble. It's actually the component level experiments. And this is for the validation purpose. And we have a target system, endpoint level system, and the downsizing, downgrading the level of the system in order to check the validity of our computer model. So this is what we call the component level experiments. In this case, we introduce a simpler geometry than the real thing. In this case, we just consider separate physics instead of if there is any multidisciplinary physics. In this case, only consider a single physics in order to validate our model. So, although this is a downsized experiment, it is still expensive compared to the bottom level. So we have less data than the number one. Third level is they call the accreditation experiments. It is still not the target system. It is still the subsystem. And for these experiments, they say they have a dual purpose. One is to test functionality, to validate their design, not just a validation of the computer model. And this is carried out regardless of what we do. This is the thing that the people must do when they develop something. So at this level of experiments, they test their functionality, and at the same time, we can validate the model. So we can afford only one or two cases with these experiments, very expensive. And based on these experimental data, our goal is to assess the reliability of interested response in the target system. And this is the problem. And for more details, you can find in this paper. Very simple, one-dimensional heat conduction, transient heat conduction problem. And at the left side here, a certain amount of heat flux is provided. At the right side, heat is insulated. And initially, there is a uniform initial temperature. And we can solve this problem even with under the undergraduate level. We are familiar with solving this problem. And the goal is to estimate the probability that the temperature at the left end, it will undergo the transient behavior starting from this temperature up to 10,000 seconds, it will vary. And at the end of the cycle, what we want is the probability greater than 900 degrees should not exceed 0.01. And if the computer model is accurate enough, we will have the confidence on this. But if the computer model is not validated, is not reliable enough, we cannot have confidence on this result. This is the thing. And they provide the experimental data based on the guidelines, the previous slides. First, material characterization. About what? Here, when we say the material property, we see K, rho Cp. This should be accurate. So we measure. And they provide the data for this. Second, component level experiments. I told that is ensemble experiments. in this case, the temperature, in this case, they prepare specimen or subsystem level problem based on this graph. For this, it's not easy to explain. You can think about this validation experiment. Originally, they prepare the downsized system and manufacture that and make experiments. But in this case, it is like this. They prepare two different sizes of width L. And they impose the heat flux with these two magnitudes. So we have 4 different configurations for the purpose of a validation experiment. And we would like to validate this computer model based on this experimental data. This is the validation experiment. And the third is the accreditation experiment. This is, I told you, this has a dual purpose, 2 purposes. One is just to test its functionality, and the other is to validate this model. In this case, this experiment is made at this point. The meaning of this point is at this length, width, and we impose this amount of heat flux. And they experimented this and got the data. So we also use this data for the validation. So we have a total of 5 different configurations data. I cannot finish all the materials in this lecture notes this time. I will continue in the next class. So until the end of this class, I will explain this. So what we get, what we have for the experimental data are as follows. But the problem introduces also the 3 different sets in terms of size of the experimental data. The purpose is to let the participants to study the influence of the size of the data in their validation. When you have a smaller size of data, the validation results will not be as good. And we have a large number of data that will be much improved. So the problem aimed at that kind of a situation for the participants. So low size data, medium size data, high size data, for the material level, component level, accreditation level, they provide this number of experimental data. At the material level, the measured data for thermal conductivity and rho Cp are given as follows. Small size data, medium size, large size data, and also they measure the values at different temperatures. Next was the component level experiments. As I explained in this graph, 4 configurations at the component level. And the reason that we imposed the lower level heat flux was, as the paper says, because the imposing higher level of heat flux is expensive. So in order to avoid the costs, you can think the reason why they experiment at this level is to save the money, the cost of the experiment. Nevertheless, you can think these 4 configurations as the component level experiments for the purpose of validation. So I will continue explaining this in the next class.